Hey, this is Avi Gutman with another Ask Me Anything event brought to you by quantreasoning.com. I invite you to join me live next time. We do this every Saturday at 11 a.m. Eastern, and you can attend for free by starting your free trial at quantreasoning.com. Okay, really tough question, especially given that there's only 2 minutes per question. We are given the relative order of these three items on the number line. So you've got z to the power of 4, y squared, and x. And I'm also going to put 0 in a cloud to the left of z to the power of 4, because we know that anything to an even exponent has to be at least 0. So 0 is somewhere there to the left or at, right? It could be that z is 0. And if you're American, I apologize, I mean z to the power of 4, or z for the rest of you. The question is asking me to check whether each of these Roman numerals is possible. Is it possible, given what we know about the relative positions of x, y squared, and z to the power of 4, given that, is it possible that each of these Roman numerals is true? Now, if I ask you to choose the easiest one to evaluate, which would you choose out of 1, 2, and 3? Which one do you think is easiest to evaluate? Well, the good news is we don't actually have to concern ourselves with whether it must be true or could be true. I mean, anything that must be true could be true. Not anything that could be true must be true. But that's an easier question in a sense. They're not asking which of those must be true, they're just asking which of those could be true, which in a way is easier. Is it possible that x is to the right of y and y is to the right of z, given what we already know? And yeah, many of you are saying that that one is probably the easiest to evaluate, and I agree. The way that I would do that is maybe I would just say that x is 1,000,000. Right, I'm just grabbing some enormous number because that kind of works for the first Roman numeral. So x could be 1,000,000. And then under what circumstances would something squared be greater than something to the power of 4 when also those bases are in that same order? Many cases, right? We could say that y is 100 and z is 1 or z is 0 or whatever, right? If we say z, y, and x, and we'll call them, like I said, 1,000,000, and this could be 100, and this could be 0 or 1 or whatever. Not very hard to see that it's possible. It's possible that x is to the right of y, which in turn is to the right of z. And that means that I can eliminate answer choice D. And this is my strategy in general for Roman numeral questions. I'll decide which of the statements is easiest for me to evaluate, then I'll start with that one, and then I'll eliminate answer choices as I go, because sometimes by the time I get to the toughest Roman numeral to evaluate, I've already eliminated 4 answer choices, and then I don't actually have to evaluate the toughest one. So that's why this is a good strategy. So I eliminated D because it was the only answer choice that didn't include 1. Now, looking at the remaining 2 Roman numerals, which do you all think is going to be easier to evaluate? Off the top of my head, I can't say which of those is going to be easier to evaluate, so I'll just go with 2. 2 is asking whether it's possible that the relative order of x, y, and z is actually the opposite of x, y squared, and z to the power of 4. Is it possible that it's the opposite? So now I can't use 1,000,000 for x. That wouldn't be a good idea because I actually want x to be the smallest of them all. This is what statement 2 is asking. Is this possible? X is between y squared and y such that y is greater than y squared. That's what it's asking. Y is to the right of y squared? Like, how does that happen?
When y is a fraction.
Very good. So if y is a fraction, then for sure y squared would be to the left of y. But how do you put x in between them? I mean, we could just say, hey, how about if this is half, then this is a quarter, and make that a third, and you're good. So that's what this second Roman numeral is testing. It's testing whether we know that when you take a positive fraction and you square it, that brings it down. It brings it closer to zero. Now, why does it bring it closer to zero? Because you're taking it and you're multiplying it times a fraction. Anytime you multiply something times a fraction, you go closer to zero. That's always true, right? Anytime you multiply a number by a fraction, you go closer to zero. Now, in this case, if the original number was a fraction, you're multiplying it times itself, then you're multiplying it times a fraction. It's going to bring you closer to zero. So y squared would be closer to zero. Let's put 0 here. There's 0. Y squared would be closer to 0 than y is anytime y is a positive fraction. Is it possible that x would be in between them? Sure. Just pick some fraction in between them. Now, we're not done with the second Roman numeral. We also have z there. So we know from the information that they provided us with that z to the power 4 is somewhere there to the left of y squared. Is it then possible that z itself is here? Again, z would have to be some positive fraction. But is it possible that you took a bigger positive fraction? I'm now thinking about z versus y. Taking a bigger positive fraction and ending up with a smaller positive fraction when you raise it to the power of 4. If it was z squared, I would say no, impossible. Whichever positive fraction was the bigger positive fraction will still be the bigger positive fraction when you square them both. Because you're multiplying a bigger positive fraction by itself versus a smaller positive fraction times itself. The bigger positive fraction will still be bigger when you've squared it. But here we have different exponents. The smaller positive fraction, we're only multiplying it times itself once. The bigger positive fraction, we're multiplying it times itself 3 times, essentially, right? It's z, the starting point, times z times z times z. So I don't know that you need to test cases here. In my opinion, you don't. In my opinion, you just have to think abstractly about the fact that, yeah, if you're multiplying it times itself more times, of course you could end up smaller even though you started up bigger. Because every time you multiply by a fraction, it brings you closer to 0. Now, if you wanted an actual case to look at, we could make this half and this a third. 1/3 squared is 1/9. 1/2 to the power of 4 is 1/16. It checks out. And then I would make this, a quarter. So x is a quarter, y is a third, and z is 1/2. It checks out. I want to be clear here. In my opinion, and let me know if you disagree, because it's perfectly fine for you to disagree. But in my opinion, if you have to test cases here, then you shouldn't do this question. You should guess and move on. That's my opinion. If it wasn't a 2-minute per question kind of test, that's a different story. But I think the reason they designed this question the way they did was to differentiate the people who can analyze this abstractly and feel confident that, yeah, if you take a bigger fraction and you end up multiplying it times itself more times than some smaller fraction, you could very well end closer to 0. They wanted to differentiate those people from the people who can't do that kind of reasoning abstractly and have to test cases. And in my opinion, you shouldn't test cases in a question like this because it's just not that kind of test. I think it's an inappropriate solution for the GMAT. Again, I welcome disagreements. I think it's not necessarily true, but that's my opinion. It's the wrong move to test cases here. Although it didn't take me that long to test those cases, but I'm also very experienced. And so I kind of knew which cases to test because I get it, because I get the concept that they're trying to test here. And I'm not confident that my students would as quickly and as accurately be able to happen to choose those cases that work. But if you're able to follow the reasoning where I say that looking at 2 positive fractions, it's absolutely possible for the larger of the 2 to end up smaller than the 2 when you raise the larger one to the power of 4 and raise the smaller one to the power of 2. If you're able to follow that reasoning, that I think is what's being tested here. The understanding that, yeah, on the one hand, it's a bigger fraction, but on the other hand, I'm multiplying it times itself, times a fraction, more times. So yeah, it absolutely could end up smaller than the smaller, the fraction that started smaller and then ends up bigger because you're only multiplying it times itself once. You're only squaring it. Before I go to the third Roman numeral, I just want to share with you something that I think helps me to think about that second Roman numeral. Like how do I think about that? And it reminds me a little bit of the concept of Halflife, which we're probably most familiar with from radioactive material. Radioactive material has a half-life, and it's defined as the amount of time that it takes for the radioactive material to be cut in half. Radioactive material decays over time, and different types of radioactive material have different half-lives. And again, what is a half-life? It's the amount of time it takes for half the material to decay. And if you think about this mathematically, you have a geometric sequence. You keep multiplying the amount of material by half every half-life. Let's say, for example, the half-life is 30 years. So every 30 years, the original amount of material that you had gets multiplied by half. And you have a geometric sequence which never really quite gets to zero, right? Because you just keep multiplying by half, so it does get smaller exponentially, but there'll always be a little bit left, even after 1,000,000 years. And when they talk about contaminated city, like what happened in Japan with Hiroshima and Nagasaki, there's a certain level of radioactivity below which we're safe. Right? But it's never going to be zero, but we need to get to that point below which we're safe. And that's what this question reminds me of, this idea of a half-life, because if you multiply by half more times, you'll end up smaller, of course. Now, in this case, maybe they're not both half. One is bigger than the other. Maybe one is 0.5 and the other is 0.51. But of course, if you multiply the bigger fraction, the 0.51, times itself many more times than you do with a 0.5, you'll end up much smaller. And that's kind of abstractly or conceptually, that's what's going on in my brain when I say, yeah, of course, the bigger fraction could end up smaller than the smaller fraction when you're raising it to a greater power. Right? That's really the concept that they're testing here. And again, I think that's like if you're not able to do that reasoning, then you shouldn't do this question, because you'll just end up wasting time and energy. It's a long test, so we don't just want to conserve time, we also want to conserve energy and ink. So the third Roman numeral. So again, what do we know? We know that 0 is in some kind of cloud here to the left, or at z to the power 4. Here's y squared, here's x. That's what we know. We want to know whether it's possible that x is the biggest of the three. That seems to me like a no-brainer. Yeah, just make it 1,000,000. Like, I feel like that part is very easy. Just make x an enormous number, make it infinity, whatever. So then the real question with that third Roman numeral is it possible that z is to the right of y, given that when you raise them to these powers, it ends up to the left of y? In other words, is it possible that on the one hand, z is to the right of y, on the other hand, this? Is that possible? I think I liked what you said about negatives more. Like, I think that's really the key to proving that the third statement is possible. I mean, all I have to do really is say that 0 is here? No. Here. That's better, right? If 0 is there, it's very easy to see how y squared could be greater than z to the power of 4. In fact, why don't we just say z equals 0? Isn't it possible that z equals 0? If z equals 0 and y is less than 0, you're done. Any such scenario will make the third Roman numeral true. Isn't that right? As long as x is 1,000,000, z is 0, and y is some negative number that's more than negative 1,000. It has to be somewhere between negative 1,000, because The reason I say negative 1000 is when you square negative 1000, you get 1,000,000. And then y squared and x would be the same number. But as long as y is somewhere between negative 1000 and 0, and z is 0, and y and x is 1,000,000, you're good. So the trick there was to use the fact that the farther you are to the left of 0, when you're squared, you pop over to the right side of 0 and you're even farther, assuming, of course, you're more than 1 away from 0. Hey, I'm just going to interrupt my own video for a moment here. If you're finding value in this video, please let me know in the comments below. And give this video a thumbs up. It really motivates me to keep uploading a new video every day. Alright, back to the video. I think that it's a really tough question. I think that, again, testing random cases is not an appropriate solution on the GMAT. But testing cases abstractly, if that makes any sense to you. So in other words, I'm not thinking about actual numbers. I'm just thinking about kind of ranges, right? Or like what would happen when the actual values that x, y, and z represent look these different kind of configurations in the number line. So I'm keeping it kind of fairly abstract. And I think that's really the only way to get to the right answer, which is E, in a 2-minute kind of time frame. I actually think that if you're a visual person, then you are probably better off using number line reasoning and those types of things than algebra. Because algebra doesn't really have anything visual about it. And that's one of the many reasons why I launched quantreasoning.com, right? Because it's like everything you see out there in terms of test prep, at least everything I've seen, is very algebra heavy, and it kind of misses the point of the GMAT, which is to test your reasoning, not your math. So yeah, I think if you can draw such number lines and do the kind of reasoning that we did here, then this question is a question that you should solve. And if you can't do that reasoning yet, maybe a month from now you will be able to, right? I mean, that's kind of why we're here, is to improve our reasoning. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.